Okay, welcome everybody. It's good to see so many familiar faces out here in the audience, and thank you for coming in today to join us. We were lucky enough to get a stop on the Jacob Racusin World Tour. We got a great presentation for you today. If you haven't had the pleasure of hearing Jacob speak, you're in for a real treat today. We're recording the session today, so we'll do the presentation, we'll hold the Q&A until afterwards, and I'll pass around the mic, we'll do some question and answer, and then hoping you can stick around for a few minutes. So I'm going to give a quick, short introduction here. Many of you know Jacob already, but Jacob's the co-founder and director of Building Science and Sustainability at New Frameworks up in Vermont. He's also co-creator of BEAM, the embodied carbon tool. In addition to his formal roles, he wears many hats. He works one of the founders of the Bio-Based Materials Collective. He does a lot of advocacy work for policy advocacy for people, planet, and he's a musician, and he does a little bit of everything. So a great person to have. So thank you for coming. So I'll stop talking now and give us a warm welcome for Jacob Racusin.
I got this. Thank you, John, Jack, thank you, Chapman, for giving me the opportunity to share some thoughts and ideas with you all. It's a real honor and pleasure, and I really appreciate you all being here. I don't take for granted taking time out of the workday and what it takes to actually gather together in real time, in real space. It's after lots and lots and lots and lots of Zoom presentations. I'm just very grateful to be in physical presence with you all, so thank you. So I'm going to tell a story in sort of 4 chapters, 4 sections here. I'm just going to launch into it. I guess the one thing I'll say, some of you have seen me speak before. Thank you for coming back. I appreciate it. I am going to be giving I'm going to cover a lot of content relatively quickly. So I don't want you to feel anxious that you have to internalize and absorb everything. I'll be presenting a lot of resources at the end. I'm going to move through it relatively quickly, partially to keep on time and partially so we can just have more discussion either right afterwards or upstairs. But don't fret about needing to absorb everything or capture pictures of all the resources. This will be recorded. I'm happy to share the slide deck, sort of let it wash over you. I'm aware of the fact that there's a really broad range of experience and prior knowledge around what I'm going to talk about. So I'm going to cover some introductory stuff, and I'm also going to kind of get into the weeds. So there'll be a little something for everyone. Just want to set some expectations so that if you're starting to feel a little flustered that I'm moving too quickly, it's all right. You can just watch the video again in 1.5 times speed, and it's going to be great. So I'm going to just launch us right in here. So I'm going to talk about materials, and I'm going to be talking about this from the perspective of climate impact. But as you'll see, that's actually quite broad, and we'll be trying to cover a whole lot of different bits of content and weaving it all together. That's why I'm going to be talking about so many different things and drawing a through line between them. So that'll be the focus. I'm going to start by talking about the energy-carbon nexus, the relationship between energy and carbon emissions or greenhouse gas emissions, and particularly embodied carbon, and how we can start looking at them and thinking about them together. Carbon storage and the time value of carbon. That's where it's going to get a little bit nerdy, but also super, super important as we expand our ideas around carbon flows and our relationship to carbon in the built environment. Regeneration at scale. So what does this look like in taking some of those principles and bringing it into practical application and moving it from boutique niche applications to broader industry transformation? And in the end is how we actually all collectively work towards achieving industry transformation as a community and as an industry. So that's where we're going. Let's start with the energy carbon nexus. And apologies, I don't have a other monitor here, so I'm going to kind of keep doing this so I make sure I know where I am. So this is to level set the first couple of slides here to make sure we are all on the same page around how we think about buildings and the built environment and its relationship to climate impact. And probably the other last thing I should say is if I say something that you don't understand what that word is or use an acronym that I haven't defined, please interrupt me and raise your hand or be like, just call me out and I will explain that. I'm going to try to hold diligence around making sure we all know what I'm talking about, but give me that feedback so I can answer clarifying questions. I want us to all understand these terms. So I want to start by just defining a bunch of terms. When we think about historically the building's relationship with climate impact, that usually relates to the emissions associated with making energy to run our buildings. And so that's this operational energy and water part of the life cycle. But as we can see, in the entire life cycle of what it takes to put a building into operation and then through its life, that's only one part, and it's not even the beginning. So we really start the clock at the extraction of raw materials out of the ground or from wherever the provenance of those raw ingredients come from. The process of extracting those materials, transporting them to a manufacturing facility and manufacturing those into products, we call that the product phase, the material emissions, A1 to A3 if you LCA nerds, you don't need that information because you already know that. So this is that first stage that combined with the process of bringing all those materials to the site and building those materials, or combining those materials together to create buildings, all of that together is upfront carbon. So that's essentially the carbon footprint of the building at day one of its operation. Those emissions are already in the atmosphere. All of that impact has occurred because of decisions that engineers and architects and builders have made around creating those buildings. Others too, I'm just calling us into our participation in that process. Cradle to gate, you'll hear that phrase too. That is the product stage. That's the gate being the factory gate. So a lot of the analysis I'll talk about is within those boundaries, and we're looking at material emissions or product emissions. In low-rise construction, which is where I do a lot of my analysis, or where these numbers come from, that's the lion's share of the emissions over the life cycle. So there's a lot of focus that gets paid to that, and a lot of the data we have is for that phase. Moving forward, now we're in the building. The building is on and operated and occupied. There's use and maintenance and repair and refurbishment, interior fit outs and mechanical replacements. You'll see those repeating over the course of time. But typically there's less materiality going into the building during its use phase, but a whole lot of operational energy and water. This is not included in our definitions of embodied carbon. So we look at the operational energy separately from all the other emissions of buildings. And what we're going to talk about is how we look at both of those sort of together in dialogue and balance in relationship. Just finishing out the life cycle here, the end of life has its own emissions, deconstruction and demolition and transport and processing and disposal. Often a lot of greenhouse gas chemicals that are released from materials themselves that may be bound in those materials, as well as the energy that it takes to process the end of life of a building. There's a D phase here that's not shown, which is like recycling and reuse of materials, which is the end of one phase, which is the beginning of the next. So if you've heard of circularity or the circular economy or circular principles, that is taking this unidirectional take, make, waste sort of paradigm and bending it around into a circle and seeing the outflow of deconstruction as the inflow of new materials to the next building. I'm being hyper simplified here, but just making sure that that concept is in play. So when I use the language embodied carbon, it's actually shorthand for embodied carbon dioxide equivalent emissions, and that's too many words to use. Embodied carbon really technically refers to this entire life cycle, again, except for the energy and water. But often it'll be used to just describe one part of the life cycle. So if we're just saying we're just looking at the product stage, that word will be used for different parts of the life cycle, which is where this all gets really confusing. Even the word embodied is confusing when we start talking about carbon storage. And so I'm going to acknowledge the confusion around the language and to say, again, if anyone's confused around terminology that is legit, please ask for clarification so we all know what we're talking about. And this is why I'm taking a minute to just define some terminology and some boundaries and principles here. Oh, yes, so CO2e, I want to define that. So when you see that little E at the end of the CO2, that stands for equivalent. So to get an actual metric, like a single unit that can quantify the emissions from any part of these processes or the whole process, it's not just carbon dioxide. That's not the only greenhouse gas that's getting emitted. There's methane, there's all sorts of propellants that can be incredibly potent. There's a whole constellation of chemicals that we release, but it's really complicated to try to look at all of those individually. And so we need a common unit to bring all those greenhouse gases together in a common unit. And so the equivalent part means that, take for example, methane. Methane has roughly 25 to 30 times the impact, let's say 25 times the impact of carbon dioxide over a 100-year period of time. And so the CO2e, the equivalent value is 25. So that means we can add up all these different chemicals in a common unit. So when you hear me say embodied carbon or carbon emissions, and I'm telling you it's actually shorthand for carbon dioxide equivalent, that really just means all of the greenhouse gases. So if you ever hear greenhouse gases or greenhouse gas emissions, it's the same thing. We're talking about all of the gases and their sort of unified emission impact. Good so far?
Just quickly, because you have these percentages, how many years did you consider
Oh, great. This is over a sort of a typical 60-year time frame. Yep. And again, this is particular to low-rise construction, and these numbers will change radically depending on your building to building, certainly typology to typology. So do not take this as gospel. Other questions? Good to go? Oh, sorry, and the question was, I'm repeating back for the home audience. What was the question? What did I just answer? What did you ask me? Oh yeah, the lifespan that we're estimating here is 60 years, which is the typical lifespan for conducting a life cycle assessment. It's not expected that the building will only last for 60 years. We just kind of pick a number to standardize how buildings can be assessed and compared to each other. Okay, so start with some of the basics, but just make sure we're all on the same page. This is stuff that we are already doing and know how to do well. So when I work with builders for climate action, we do a lot of research, and a lot of our focus is on the residential construction side of things. So you'll see some references here to low-rise residential, but the principles apply to essentially all buildings with some exceptions. So if we look at a two-story house in Toronto that has an energy mix of natural gas for heating and hot water, and then plug loads for electricity for lighting, and plug loads and cooling, and built to code minimum efficiency, a typical Toronto building is going to release about 3.5 tons of emissions per year, and that's year upon year upon year upon year. So over 30 years is about 100 tons of emissions. And so that's sort of the business as usual case. And the work that we've all been doing as an industry for like generations now is to reduce the energy loads, and then more recently to get off of the more emission intensive fossil fuels into renewably powered electricity to reduce the emissions that come from the energy that we're consuming. So we turn this into a high efficiency building, improve the enclosure, reduce the loads, and switch everything over to electricity. Toronto's grid is relatively green, and so, or low emission, I'm trying to be a little more accurate. And so that really reduces the annual emission profile of that building, and so it's a huge reduction in emissions. We know how to do this, we know what the strategies are. The real challenge we have now is just doing this all the time for all of the buildings. And all this language around scale and industry transformation and the electrification revolution and transition, that is what this is. There's always new technologies and new approaches and new ways of getting there, but this is what our task has been for a while. It is absolutely critical and imperative that we continue along this path. And also, this is not an accurate graph, because we don't actually start at zero, and we don't start on the day one of operation. As I mentioned in the last image, there is a footprint to the building when we start the operational phase. And if we're trying to set goals around decarbonization by, say, 2050, we need to know what this is to actually know what our emission profile is by the time we hit 2030, 2040, 2050, whatever number we're trying to get to. So that becomes part of a pretty critical part of the analysis that we need to bring in if we're trying to reduce these loads and switch over to electricity for the endpoint goal of reducing our emissions. If that's our goal, we need to have our analysis boundary wide enough that we know what that initial footprint is and address that as well in our strategies. And so that's where these material carbon emissions come into place. That's really the upfront emissions. It's transportation and construction as well. And it gets a little more complicated to do those last two phases. We can talk about that over beer or Q&A. But suffice to say, those upfront emissions, plus not only the energy that we're using, but the energy source emissions that are released from that energy. Those are all part of the equation. So for a long time, energy was a proxy for climate impact. And it's just not that simple. That is critical. We definitely need to bring our loads down for a host of reasons, and we'll talk about a bunch of them. But where that energy comes from and what the emission profile of that energy is also crucially important. And that's where the electrification movement and then bringing down peak loads and a lot of the nuances and details around electrification show up here. And then all those other upfront emissions are all necessary to understand what our carbon intensity is and to hit our near-term climate reduction goals. So we also have data to back this up. It's not just theory. We have studied this repeatedly over many different buildings, and we consistently see the same results, that it's not until we're reducing both the upfront and particularly the material emission profile of our building, as well as the operational performance and the energy behind that building. If we're not solving for both of those problems, we really just don't get to low carbon outcomes. So there's data to prove the thing I was just talking about. So I want to call out some of the confusing, I'm going to try to be generous and diplomatic here, and I'll see how long I can keep that going. Some of the confusing analysis I'm seeing in the marketplace that I want to address directly, because this is getting more confusing as we move forward in time, and that is a major risk to adoption, to making change. Anyone that has been on the sales side of this whole, building world, or really anything, the number one barrier is confusion. If someone is actually fired up in an opposition, like, oh, wait, there's an entry point, we can talk about this, that, or the other, but if people are just confused, it is a barrier to taking action. So I want to talk about some of the confusion that I see in the market, which is this. I'll often see analysis like this, that we've got year upon year upon year operational emissions, and then there's an upfront emission line that gets drawn across, and then we look for that point where there's a crossover point. Let's say there's a balance point, or even worse, payback after 10 years. How do we use that information to make good decisions around decarbonization? Right. I don't think it is useful. I think there's some very specific cases, maybe around material reuse, or let me say it this way. If you need to figure out what that balance point is, you've already lost control of a whole lot of the conversation around the outcome of the building.
Balance point's in the past.
That's a great way to describe it. Yes. So if you are seeing conversations around this, be critical as to why, what is this frame, and what is the information we're supposed to be getting out of this. This is also not technically accurate from what the atmosphere is experiencing. The atmosphere sees this. We're starting at this point and then adding more, and we don't get to zero until we reduce both. So I want to try and simplify some of the noise around trade-offs and balance points. I see a lot of this coming in the conversation of insulation. We need to solve for both problems and get to zero across these various timescales. And just want to float that out there to try to dispel a lot of the confusion I'm starting to hear now that these ideas are becoming more socialized, and we're all trying to figure out the relationship between materials and energy. So that's number one. We can talk more about that if you all like, but put that down for now. So I want to look more explicitly at some of the strategies that we've been using to reduce operational emissions, and then how that relates to the embodied emissions that come along with some of those strategies. And the TLDR here is that in pretty much every case that we've found, there is at least an opportunity to significantly mitigate the embodied emissions from the materials that are being used to reduce our operational energy, if not actually reduce both. And it's just a matter of developing strategies that really hold the whole and are considering both the embodied and the operational emissions. My favorite one is reducing building size and surface area. Do we need to build the largest building that our budget can afford, or do we build the smallest, best building that the programming requires? We don't always have the opportunity to ask that question, but for those of you that do, that is a fundamentally important question. And then, does the building have to have 18 corners? Could it have 10 corners? Could it actually have 4 corners? This is the hero architects in my eyes are the ones that can take simple buildings and make them look incredible. Because that's the category where we know that by having more corners, we are increasing thermal bridging potential, we're increasing disruptions and air bypasses in our air barrier. We are absolutely increasing the cost. When I was in construction project management, we would often do our pricing not by cost per square foot, but by lineal edge of construction, because that's where all the construction costs go. On the materials side, we're consuming way more materials for that complex and increased surface to volume area, as well as the amount of waste because of all of the weird sizes and shapes, and the waste profile goes up significantly. So if we can solve for waste, embodied carbon, operational energy, operational carbon emissions, and cost with the same move, those are the strategies we need to identify early and lean into. The win-win-win-win-win strategies are crucially important. And so it needs to be a much better justification for why that building has 4 different roof profiles and 18 corners if it's causing penalties all along the rest of the pipeline. Insulation is another really interesting one. There's a version of the story where we are consuming more insulation to reduce the operational emissions of our building. That insulation has an embodied emission profile, and so that number goes up. If we recognize that there is a potential conflict there, that compels us to spend a little more time and energy to find a lower emission insulation, or maybe even an insulation that actually stores atmospheric carbon, and win in both of those categories. But we have to identify that we need to solve for both of those problems early enough to bring that into the strategy. We can keep going on down the list. I'd actually be happy to go down the list. I'm a little worried about getting completely distracted and blowing our time entirely, so I'm going to keep moving forward. We can talk about windows and air tightness, all these other things. I am going to talk for a minute about mechanicals, because that's fascinating as we are seeing the proliferation of heat pumps entering into the market to be able to support the electrification process and solve for the energy and operational emissions side of the equation. Those of us, I have a mechanical design background. I've been studying the emissions of MEP equipment pretty heavily the last few years. And there's another win-win-win scenario that shows up here, which is that the old rule of, the old approach for sizing equipment was to significantly oversize it to make sure there weren't callbacks and everyone has all the heat they need in the wintertime. What we are finding now is when we oversize heat pump equipment, it has really negative consequences on occupant comfort, has very negative consequences on the energy efficiency of that equipment. The oversizing can lead to short cycling, which will depreciate the life cycle of that equipment, so it becomes more expensive and needs to be replaced more frequently. What we also see on the embodied side is you're using more equipment, which is typically pretty intensive, like really emission-intensive circuit boards and metals and highly processed equipment. Those larger pieces of equipment have greater refrigerant charges and often much more complex refrigerant distribution systems within the building, like larger and more complex VRF systems. What that means, refrigerant has some of the highest CO2e ratios of any of the materials we use. Our 410A, which has up until recently been sort of the typical refrigerant for smaller systems, is 2,100 times the impact of a molecule of carbon dioxide. Now, the greener versions of those refrigerants are down to like 700 times the impact of CO2e. Of carbon dioxide. So like refrigerant is a really, really big deal. Now we're converting all of our buildings to be on refrigerant powered systems. So if we're oversizing those systems, we now have more refrigerant that could potentially leak, but as they get more complex, there's more potential points of leakage across that distribution system. And so as we reduce and right size all of that, we're also solving for these embodied carbon emission problems that are associated with heat pumps. So again, win, 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 win. By revealing that value, it can compel us to spend a little more time on mechanical sizing and right sizing the mechanical system. Maybe even moving from a VRF distribution, a refrigerant-based distribution, to a hydronic-based distribution, which not only reduces all that refrigerant, but makes controls easier and reduces the risk around oversizing, particularly on the cooling side of things. So again, all these like points of alignment, but if we don't recognize that they're aligned, they're really hard to defend when you're trying to usher a project through all the stages of design and all of the associated like sort of first cost filters that tend to make a lot of these optimization opportunities fall by the wayside as we go through the complexity of bringing real buildings into the real world, let alone the replacements. Because remember now, if we're short cycling a piece of equipment that goes from a 15-year lifespan to even a 12-year or 10-year lifespan, that means you're just repeating that entire consumption and disposal cycle again and again and again with that much greater degree of frequency within the lifespan of the building. So there's a lot of alignment here. This graph should look pretty familiar. This is a very typical graph around cost, and the best way to address cost in a project is very early on, where you can make the greatest number of moves for the least amount of effort. We've also seen this. I have an energy modeling background, and this was like sort of drilled in. Oh, that last little part. Imagine this continuing. I'm not quite sure why that didn't show. Maybe it's white. I don't know. Anyways, apologies, but you can imagine that continuing along there. Very similar with energy efficiency. Anyone in the passive house kind of community here? Some nods. Okay, so anyone whether it's passive house or net zero or whatnot, anyone's been in the experience, and those of you in the construction space, I imagine, have probably heard this. We're like, all right, our building's basically done. It's the end of DD, or like you're looking for some like feedback. Can we make this a passive house building now? No, you can't. Like that ship sailed like an entire phase ago. That was 3 months ago. We could have said no problem, but now really expensive to try to implement that, right? It's the same thing with all this carbon reduction. It is really so the first question is, if you have the agency to say, do we actually need to demolish something and build something new, or can we work with what already exists? The lowest carbon building is the one that's already there. With some exceptions, but for the most part is a general principle. So anyone that has agency of even being able to answer that question, that is the highest hand on the lever we have. If it's adaptive reuse of existing infrastructure, that all the emissions of its construction are already in the atmosphere. From that point, yes, does it have to be enormous? Does it have to be complicated? do we have agency in, from a design perspective, reducing that impact? And I'm going to say that's not just for designers. I've been on both the construction and design side of the table in a lot of these project development meetings, and it is very frequently folks with real world construction experience that bring some of the best brilliance to the design table around how to optimize around simplicity, or where there's both a win around both cost and environmental performance by simplifying a design. So this is not just for designers in the room. This is for all you CMs and construction-minded folks that may be able to have input here too. And then building clever is just, like, can we simplify the structural grid? Are there, are there mechanisms we can use to dematerialize the building, saving cost and also saving materials at the same time? By the time we're trying to look at, like, what is the right insulation product to use or what's the best cladding, I'm not saying that's bad. Like, we can make enormous benefits in just optimizing for the best drop-in replacement of a high emission material for a low emission material. But your options are down to here. Like, right, you're like, so many decisions have already been made. There's only so many more decisions left to make if you're only looking at materials. But that's a great place to start. So if you're new to all of this, simple one-to-one material substitutions is a great walking in the doorway to explore what are my opportunities on the material side. And the further up the line you go, the more opportunities there are available. And this is if there's ever been a justification for the value of integrated project development and bringing construction and design knowledge into the project development process, it is this. So there's yet another value, not just in project efficiency in terms of its delivery and making sure that what happens in the field is actually what's represented in the drawings, but also to be able to really optimize for carbon reduction.
John's a good pitch for your after. You want to talk about materials?
Would this be a good moment?
Just like 2 seconds.
Yeah. Public service announcement.
Yeah.
So we're going to stop by the, we've got a bio-based materials petting zoo on the second floor, and the name is, I think, I don't know, was it James or you? Or somebody came up with the name, but anyway, we've got a whole corral set up upstairs with a bunch of bio-based materials that we could stop in. Yeah. You can feed them, you can pet them, just don't take them with you.
They don't bite. Exactly. All right. I'm not going to take questions right now in terms of like, well, what if, but is there anything that I should define or explain? Cool, the level setting has been done. We're going to go a little bit deeper now, talking about carbon storage and bringing time into the equation around when emissions occur and how to manage that extra variable. This will get a little bit nerdy. For those of you that are looking for that, let's go. For those of you that are already a little confused, it's all right, just let it wash. We're going to zoom all the way out. Some of you have seen this, some of you have not. It is very relevant for me in thinking about this to identify that we are part of a global carbon cycle in which carbon is flowing into and out of a half dozen different pools in our planetary ecosystem. There's been a lot of like fighting carbon, a lot of like violent language against carbon in our like attempts to address climate impact. Like, I'm going to invite us to reframe carbon as an integral part of like planetary existence and survival, and that it is a resource that flows into and out of various states that we have just not been we've been very poor at managing and intervening in very negative ways. So to explain this in a little more simple terms, when we've been thinking about, again, the built environment's relationship to climate impact, it's been like this left side of the image here, where you've been extracting carbon reserves from deep underground that used to be plants and animals. They were part of the biosphere, millennia ago, and over a long period of time and geologic pressure have been consolidated deep underground. And we are dramatically intervening with the carbon cycle by extracting it from those deep, long time cycle stores and burning it for energy, and then the byproduct is migrating that carbon up into the atmosphere. So we've been participating in accelerating a carbon flow cycle from a storage state deep underground up into the atmosphere. And the goal is to do less of this. Actually, the goal is to do zero of this. And I would say, so all of the energy management transition we're talking about in the first handful of slides, that's this, to which I'd say absolutely critical. We need to be doing more of it better and more efficiently and faster. It is completely imperative, foundational, necessary, and wholly insufficient if our goals are actually to reduce the chemical balance of the atmosphere such that human civilization as we know it can persist through the end of the century. Zero is not a sufficient goal. And if that is our goal, zero operational carbon, that's fine, but that's not actually addressing what it means for us to continue to maintain human civilization the way we know it. If that's the goal, then we need to widen the boundaries and look for other opportunities to adjust the imbalance of carbon concentration in the atmosphere. In this case, in the form of carbon dioxide and associated greenhouse gases. So I'm going to invite us into two other concepts. Does anyone know what the largest sink of carbon is on the planet? It hasn't already seen me present on this before? The ocean. Like, how much of the carbon in planetary ecosystems are in the ocean? Like 78%, roughly. Those are numbers I've seen. Like the majority, right? So if we really care about atmospheric carbon balance, then everything we can do to keep microplastics and forever chemicals and phthalates and all this toxicity out of oceanic ecosystems that are depleting those ecosystems and depleting the ocean's capacity as a carbon sink, like that's every bit as relevant or maybe even more relevant than our direct emissions. So this is how interconnected all of this work is. I'm not going to be talking about oceanic ecosystem health and plastic and toxicity proliferation in this presentation, but I absolutely could. John, question?
Just clarity, when you're talking about carbon in the ocean, are you sort of thinking about that as sort of available cyclical carbon or sort of stored carbon the way that, fossil carbon?
Oh, so the question is, like, the carbon in the ocean, is it like deep, long storage like it is in fossil carbon, or is it more cyclical? It's much more cyclical. I am not qualified to get into the details. However, I know there's numerous different capacities and rates of storage and transfer between plants, flora and fauna in the ocean, as well as within the water itself, and its relationship with the atmosphere, as well as with other pools. So it's really complex, very dynamic, but much more dynamic than the long time cycle of storage deep underground. Yeah. What I'm going to talk about is photosynthesis, the most scalable, cost-effective, and proven carbon capture and storage systems on the planet are trees. And this is known and proven. But because there isn't an economic value directly associated with that, that has not been realized as a viable market solution. We can have a whole other conversation around that over beer. What I will say is that this is something we have direct agency in. We have a direct agency over like mitigating harm here. We have a direct agency in spending billions of dollars of our consumptive power as an industry consuming products to spend some of that money on sustainably managed forests and agricultural systems that are already doing this and managing the carbon flows coming out of those systems that right now are just going back up into the atmosphere when the residues coming out of forests and agricultural systems just decompose or burn and go back. So we can positively and proactively engage in managing the carbon cycles the same way that we're proactively and negatively engaging in the carbon cycles on the left-hand side. I really get frustrated with the idea that, oh, humans are just a cancer, and if we just we're off the planet, it'd be fine. I'm like, or we could actually recognize we have the capacity to do good as well as harm and leverage that to proactively take action to decarbonize the atmosphere through investing in systems that are already doing that and manage the carbon flows of those systems well right now. So that's what I'm going to focus on a little bit. This isn't just theory. This has been very well researched. The most comprehensive research I've seen come out of the UN with a bunch of folks from the Yale Center for Ecosystems and Architecture that have done both technical and economic studies around this at scale across the globe. That's a great resource if you want a little more like meat on the bone than just my quick visual narrative around this. There's also a really strong market imperative around this. Amazon has been funding really terrific research by some very well-qualified and kind of neutral party forest industry professionals to figure out sustainable forest supply chain management because it is in their business case to do so, and it's not just Amazon. So I just want to be clear, this isn't just like environmentalists who care about this or academics who care about this. This is a very strong market drive and market imperative around figuring this out as well, just in case anyone's skeptical as to whether or not this is all just, hooey. Yeah, please.
But when they talk about sustainable, do they care about people as well, or is it just about embodied carbon?
So the question is, do you care about people as well or just about carbon? That is a great question. This report, I have to look into the details to understand how much of social impact is valued in here. I know it's broken out geographically based on different forest typology, and associated industries are evaluated, but whether there's actually, if human well-being or cultural well-being is held as a key performance indicator of success, I don't know, but that is a crucial question. I'm actually going to talk about that at least briefly, so thank you for prompting a thought that will be coming up shortly. Builders for Climate Action has, we're really committed to advancing this idea and trying to reveal the opportunities around working with bio-based materials as a near-term solution for atmospheric decarbonization. And so we recognize that if we're just talking about biogenic carbon as a big lump, we just talk about trees, which isn't bad, but it's incomplete, and we actually need to break this down a little bit further to be able to develop more granular and a broader diversity of different strategies around working with bio-based materials. So we have two basic categories that we've assigned: short cycle and long cycle carbon. And that the cycle, the short and long, is talking about temporal cycles, time cycles. So we're looking at plants that only, that are less than 10 years in their growth cycle, or carbon that's like going to be near the end of its life cycle really soon, compared to plants that live a really long time, or it could be decades through which that carbon will be going through its cycle. So examples of short cycle carbon: waste stream materials. Has anyone worked with cellulose insulation? Right? This is cardboard, right? This is a whole bunch of Amazon boxes that are destined for the landfill. Some of that may be petrified, but a lot of that's either going to turn to methane or carbon dioxide. So great, we're appropriating waste stream materials destined for their end of life, intervening in that cycle and reappropriating those materials to be long-lived building materials and keep that carbon stored in physical form out of the atmosphere. Ag and forestry residues, similarly. Otherwise, they would be going through their end-of-life cycle and cycling back into the atmosphere. We're talking about intervening and interrupting that cycle and redirecting those physical carbon stores into physical materials that stay on the planet in a building, stored in a building for a long period of time, turning buildings into carbon sinks for the lifespan of that building. If a crop wasn't going to be grown otherwise, then they wouldn't have pulled that carbon dioxide out of the atmosphere, so on and so forth. Timber is more complicated. If you're cutting down a tree for the sake of it being a building product, it's hard to know. That's a 30 to 60 year growth cycle. Would that tree still be photosynthesizing? Would it be killed by beetles or burned in a fire? Was it near the end of its growth cycle anyways? What's the impact on the rest of this complex forest ecology? It's just really complicated. That's why Amazon's been pouring many thousands of dollars to try to understand the forest ecological science and the supply chain dynamics to really understand that complexity more. So we want to disaggregate that to identify that some of these are falling off a log easy. Yes, take waste and turn it into something valuable. Like there are no counterfactual scenarios to what else might have happened to that cardboard, other than like maybe an arts and crafts project. And that has not been scaled out to be a meaningful carbon storage solution. Other things like timber, it's hard to know whether did the atmosphere benefit from that logging operation. It's complicated, and we may not actually know the answer to that with a high degree of certainty. So that's why we're disaggregating this. For those of you that are visual learners, I'm going to say the same thing again, but with pictures. We build with straw a lot, so I'm using straw as a case study here. As an annual aerial growth cycle for most grain crops. Some of them are perennials, and they're I'll move past the botany. Say annual cycle for these plants to grow. At the end of the year, all the seed heads get cut from the plant to make grain. At the end of the year, there's no version of that grain plant where it continues to grow year upon year upon year. That is a very short cycle of its growth, death, decomposition. Some of that goes down into the soil. A lot of that ends up in the atmosphere, either because of the nature of the plant or the nature of the agricultural practice. And our suggestion is, rather than allowing it to go through that short cycle, we intervene, grab that carbon before it goes back through its end of life cycle, and turn it into the beginning of a building material that will now be captured for the lifespan of the enclosure of that material. In the case of insulation, if it's insulation, it is also reducing the operational emissions by providing a high-quality insulation solution. It is also displacing mineral or petrochemically intensive insulation products that might otherwise be used. So like win-win-win. Those are strategies to lean into that have an amplifying benefit when you're just talking about a simple material replacement. We want to have less waste coming out of our agricultural systems and have more storage capacity within our buildings. So this seems really obvious and clear to us as a potentially viable, actually as a practically viable solution. I'll give you a case study on that shortly. Really different than we're talking about trees. 30 to 60 year growth cycle on the tree. Because of that, and because of various other factors, forest ecosystems are a heck of a lot more complicated than a lot of the agricultural systems that we are getting those grain products out of. First of all, would that tree keep growing or not? That's a fundamental question to ask, and it depends forest by forest by forest, and we might not even necessarily know. Forest fires are showing up in places they didn't used to before. Pests are proliferating across North America as climate is changing within this continent in ways that they haven't prior. So this just gets harder to predict. Also, depending on the forest and the product, maybe 50% of the mass of that tree may be left in the forest to decompose. Some of that may be good for forest ecology, and a lot of that may not actually be necessary to have all of that biomass just rotting away in the forest. In many cases, it's actually burned. Then there's also mill waste and kiln emissions, and so all that to say is that it's complicated. I live in a forested region. I've been on the commercial side of forestry projects before. Some of my best friends are loggers. I'm a big fan of forestry and wood products as a solution, but we have to understand the complexity, and just assigning it value is an oversimplification, and there's just a little more nuance that needs to be brought into whether or not, again, if that tree was cut down to be part of our building, did the atmosphere benefit from that happening? And that's a harder question to answer than grabbing the straw off of the ground before it gets burned. Okay, this is where I'm going to get nerdy, just fair warning. For those of you that are in the LCA community, you're like, yeah, negative emissions. Oh, so that's probably the thing to say. So in looking at all of this, we can actually quantify the amount of carbon dioxide that's been photosynthesized, look at what the equivalent, look at the mass of carbon that's in that product, what the equivalent carbon dioxide was to put that carbon into that tree, into that straw, and assign a negative emission. Like that was carbon dioxide in the atmosphere, and now it's not, and we're storing in the building. And the value of that is reflected as a negative emission. And there's a lot of LCA, life cycle assessment methodology, would say, you can't just give it a negative emission when it's grown and then ignore what happens at the end of its life. We have to presume those materials are going to go through end of life. It may not be for a while, but we have to assume it'll eventually end up back up in the atmosphere. And you can't just use the good number and ignore the bad number. Particularly if you're only counting the product emissions, it's like favoritism, it's not good analysis, right? To which I would say, yes, that's totally legit. That is absolutely an appropriate critique and really a legitimate methodology for how we think about biogenic carbon in this context. It's just not the only way that we can or need to think about our relationship with stored carbon, because this methodology doesn't consider what is happening over that intervening 60 years of time. It's just looking at a negative number at the front, a positive number at the end, that equals 0, and we're done. But this time matters. So that's what we're going to talk about for a moment here. If we're looking not just at the number of kilograms of emissions going up or going down, but we're looking at what the effect over time is on temperature change. And so the metric here is actually radiative forcing for you climate nerds. If a pulse of emissions, a ton of emissions is pulsed up into the atmosphere, it doesn't just last for a year and go away. It stays in residence in that atmosphere for an exceptionally long time if it's carbon dioxide. Other chemicals have a faster decay rate. You can see this bends down a little bit because the carbon dioxide does decay over time, but it takes hundreds of years for it to go through its decay process. So you see a long tail, and it's the area under the curve that we are actually experiencing on the planet in the form of average temperature rise. That's the effect that we're trying to address in the first place. Let's say there's another pulse at the end of life for all the demolition material applications, and so the tail begins again. If we look at this from the perspective of stored carbon, this isn't just emissions that were avoided. This is actually carbon dioxide that was in the atmosphere and is drawn down out of the atmosphere into the body of a plant that is then put into a building for an extended period of time. Over the period of time, that is a very significant impact on having that carbon dioxide removed from the atmosphere. It's sort of corollary to if it was introduced into the atmosphere. And so even if we assume 100% of release at the end of the 60-year lifespan of the building, that only has a 20% a 20% impact on temperature change based on its initial storage compared to if a ton of it was fully emitted. So that means we're basically buying ourselves. If we can buy ourselves over a 60-year period of time a way to figure out how to manage that carbon better and not have 100% of it back up in the atmosphere, this is where principles of circularity and material reuse dovetail beautifully with the concept of biogenic carbon storage so that we don't just have to throw it all back up into the atmosphere at the end of that building's lifespan. Then we have a net permanent cooling solution from that stored carbon. This impact of time really matters from the perspective of mean temperature change on the planet. It's not enough to just not add additional emissions, because what we see is the emissions that were released stay there for a long time, and we're going to see temperatures increase into the future even if we hit the 0 point tomorrow. So we need active decarbonization solutions now to counterbalance the fact that we've already overshot that planetary boundary. And that's where the storage mechanism becomes really important for us as a not just a idealistic future casting strategy, but as an immediate strategy for decarbonization in the built environment. The other thing I'll say is, if we're trying to hit goals for 2030, 2040, 2050, it makes no sense to me that we'd use a 60-year time boundary in our carbon balance to apply towards a goal that's happening in the next 25 years. So if we're not just looking at the life cycle and a 60-year lifespan as our, where we're hitting our carbon goals, we need to hit carbon reduction goals by 2030, and then another set of goals by 2050. We need analysis that actually maps to that. And if we're looking at stored carbon, it has not been re-released into the atmosphere unless you built a crappy building that only lasts for 15 years. It's still being stored, and that's really meaningful for our near-term goals. Not that it doesn't matter what happens in 60 years, but if we don't figure this out in the next 10 to 25 years, we have a very different set of problems to solve 60 years from now. So we just need to align how we're looking at this with the right time boundaries for the goals that we're trying to hit so that our strategies are aligned with our goals that are aligned with good analysis. And that's where this time value of carbon becomes really important, and not just looking at 60-year boundaries for all of our metrics around how we evaluate our carbon emissions. I know that was nerdy. I appreciate you staying with me. For those of you, I'm gonna zoom back out and look at these two different ways of thinking about counting carbon storage. The way to look at this is on the left here, we are counting carbon. And then on the right here, when we're looking at this dynamic refers to the time value of life cycle assessment. We're now looking at the value of that. What does that actually mean in terms of temperature rise? And maybe before I keep going here, well, no, I'll keep going here. I'll use money as an analogy. Yes, we need to look at the ledger of debts and credits in our, in our checkbook, but that doesn't tell us anything about compound interest or the time value of money, right? We look at money from multiple different perspectives. My background is as an energy modeler, I would never use my annual energy loads to size my mechanical equipment. I would never use my peak energy demand to size my solar system. We are used to looking at things from more than one point of analysis to make different decisions, and we need to do the same thing with how we're looking at embodied carbon and carbon emissions as well. That is better analysis. So if we're looking at how does carbon move within the system, and like what is the accounting of that across the life cycle, great. +1, -1 static life cycle assessment, totally appropriate. And if we're looking at how does the climate respond to those carbon flows, which I would say is what actually matters in terms of actionability and the purpose behind counting carbon in the first place. It's not an accounting exercise. It's because we're trying to stabilize the planet. So yeah, that actually matters, and we need to look at this time value as well if the goal is to create good adaptive strategy in the near term. Okay. Clarifying questions? I know that was a lot. I appreciate it. We can keep talking about this. Okay. Please. No, please.
You're saying that all of the mass timber project that shows that something is negative,
Mm-hmm.
they can be wrong.
Might be. Well, okay, no, it's not wrong. So the question was all the mass timber projects that show all this negative emissions, and like, where do I look? I'm gonna look at the camera. Is that wrong? I would say it's not wrong. If the analysis goal is to count up the, quantify the mass of carbon dioxide that was photosynthesized to put the amount of carbon that's in that mass timber into the building and account for that, and the decision is to give it a negative value, that's accurate. The question is that decision appropriate? It's appropriate if you say all wood qualifies as a negative emission. It was in the atmosphere and now it's not. The logical conclusion of that could be deforesting all of North America by saying we want to take all the carbon that was photosynthesized into trees and put all that into buildings. And we don't actually care about the practical output of like what that means for forests. So it's like, is that the right analysis? It's not is it right or wrong, is that from what perspective is that useful? And if we're trying to make decisions from the atmosphere's perspective, we need to ask, is allocating a negative emission for that in mass timber, is that a true reflection of what the atmosphere is experiencing because of that clear cut? And also, is it appropriate that that may now be used to justify spending more carbon in your windows or in your foundation or somewhere else in the building that is irreversible? That was a fossil fuel, now it's in the atmosphere, and like, we're not getting that back down underground. So again, it's just the boundaries of that analysis are insufficient to make good decisions. So we need to ask more than one question. And that's a hard question to answer with trees because we don't even necessarily have transparency through the supply chain to know where our trees came from, let alone to know what is the forest management practices of that forest ecosystem. And if it wasn't cut, would it stay a tree or would it be burned or would it be clear cut for development? And that's going to be really different in the Pacific Northwest than it is going to be in the forested Northeast, than it is going to be in a plantation grove in the Southeast, than it is going to be in a tropical hardwood plantation in South America. Very different technical and economic environments that are going to inform what might have happened to that tree. So the math may be right, but if the math may not be well aligned, the analysis may be poorly aligned to the goal of positively impacting the climate. And the gap between there is the responsibility of the designer to where did that wood come from? And do we want to give it a value? Do we want to show that it has a potential, but we don't know we can give it a negative emissions, or we're going to show it on the side, but we're not going to count, that's where the complexity shows up. There is no part of this that's complicated to me that says we can take straw that is being grown for food production and then take the waste material coming out of that system, and instead of having it be flooded with water that our water tables can ill afford, to force anaerobic decomposition of the straw and have plumes of methane. Nope, use that, put it in a building, give it a negative value. There's no part of me that sees any other outcome for that straw that would otherwise be negative for the atmosphere.
More arts and crafts.
More arts and crafts. More paper mache. All right, so I'm going to move us now into more practical applications of working with these carbon storage solutions. And I'm going to start by using our company as a reference case. I'm going to move this pretty quickly. A lot of you are familiar with our work. For those of you that aren't, just give you something tangible to hold on to here. This is like a third of us, maybe half, less than a third of us. This is about a third of our company. We're a 20-some-odd person, 21-person design, build, and fabrication and training firm, worker-owned cooperative in northern Vermont. We've been building with straw for 25 years or so, and I've been putting moisture sensors in those buildings the entire time. So we have a really high level of confidence of how to work with this material successfully in the Northeast. And we pivoted recently from building custom buildings to becoming a panel fabricator and now building straw and wood fiber insulated panels. So just to make this very tangible, I'll move this relatively quickly. Our design team is on our architectural team is on the Revit platform. So we will frequently work with other architects and builders to take a design, panelize it, figure out what a panel layout is for that design, and then turn that panel layout into shop drawings and fabricate that into panels. We get the majority of our straw. Our primary vendor is Aurora Farms, which is in Lake Champlain Basin. They grow grains. They're a core part of actually our regional food shed. They're one of the few grain producers, period, let alone organic grain producers in our region. They produce a variety of different both retail and commercial grain products. And I'm going to pause for a second and talk a little bit around the land use impacts of our supply chains and one of the additional value of investing in bio-based materials. So Lake Champlain is a very polluted body of water and is under serious pressure from the EPA to clean up the lake. One of the major sources of pollution are coming from ag industry. Vermont is a very well established dairy industry, and the effluent of the industry is a big contributor to what's fouling the lake. So right off the bat, the fact that we're trying to invest economically in regenerative and organic agricultural practices in this very sensitive watershed is super meaningful for us. Like, this is really important that this company survive and be able to maintain the integrity of preserving this watershed. It's also one of the most gentrified parts of the state, and the development pressures in this region are huge. The other major source of pollution into the lake is combined storm and sewer systems, these antiquated systems that are fouling the lake through development pressure along the waterways. And so by investing in a working landscape economic model that keeps development pressure away from the lake is also tremendously valuable and has ecological and economic value for our entire region. We get to contribute to that preservation by investing economically in that organization by purchasing their waste products. That is meaningful for us, and there is an amplification of the value both within our region and broader by that investment. That is not the same when we buy insulation products from multinational chemical corporations. And that doesn't always show up in a carbon balance sheet. That is hugely meaningful in terms of our corporate responsibility and our relationship to place and the investment power that comes from intervening in the supply chains from which we get our materials. We get to choose that. We have purchasing agency over that and how we choose to insulate our panels. So that's actionable for us. We stuff straw in boxes. This is not high tech. And actually, I'm going to zoom back a little bit. Just like the working model I have around our panels, it's double stud construction with compressed straw insulation. So the structural work's being done by double stud frame, air barrier sheathing. We designed this to be as like falling off a log, easy and obvious and simple from a structural standpoint, from like flashing, from trades organization integration. We're trying to make this boring and normal and normative. The only difference is that it's a different type of cellulosic infill insulation. So yeah, we stuff straw in boxes. That's it. These plywood corners come off. This is just during construction. Those panels get put up on site with a lull. We have intentionally decided to make smaller size panels because we're in rural Vermont, so we have a lot of remote sites. And we're also building, I'll talk about this in a minute, a lot of ADUs. So we need to be able to get these into backyards and urban environments, so we need small form factors to be able to do that. They don't have to be small, but we've made that choice. So we are a panelizer for other construction projects, and there's a whole conversation we can have around the industry's adaptation of panelization as a mechanism of delivering buildings. That's a really exciting conversation we can have that has also enabled us to store a tremendous amount of straw in buildings that otherwise we didn't have access to when we were literally hand stacking bales on site. We have also developed a line of small buildings. ADU size up to, I think our largest built structure is a 1,200 square foot 3-bedroom, and we're in design on a 1,600 square foot 4-bedroom, fully panelized. We work with straw because we love it and we believe in all the reasons, but we went to panelization to actually address the housing crisis, because as custom home builders, no one in our cooperative could afford our own work, and we were consistently pricing ourselves out of all of our communities. And so we pivoted away from custom new construction to be able to address the housing crisis in our region. So there's a stacked benefit around how we can organize the values around what we're building with and how we're building and who we're building for. So this is one of our little ADUs. This is actually tucked into a backyard in Burlington for a family that expanded, couldn't afford a larger home, and instead was able to put an ADU into their backyard and expand their housing within the context of their sort of quasi-urban lot. We work with a lot of native wood and local materials. Health is fundamentally critical for us. None of what we're doing holds any value if it's poisoning the people inside the buildings, and if that toxicity then percolates into the ecosystem at the end of the building's life. So we started the whole carbon flow cycle talking about if all the toxicity from all of the chemicals that might otherwise be in these finishes and materials end up in waterways that end up depleting oceanic capacity for storing carbon and ruining the atmospheric carbon balance, we've done no benefit by just putting a bunch of straw on the walls. So there's just more opportunities, and where we can see, oh, something that's good for the health of the occupant, that's also good for the health of the ecology, is also good for climate. Like, all of these things actually build upon each other and add more value without taking more effort. We're just recognizing more value behind the decisions that we're making. We also use this for commercial applications. This is a Fabulous farm, Soulfire Farm. They are a Afro-Indigenous farm that addresses food justice issues in their region and trains up BIPOC farmers for the next generation of regenerative farmers across North America. And they host thousands of people for agricultural trainings every year. And we built a program center for them, a commercial kitchen and dining facility. It's a little bit dark, so I apologize for that. But just to give a sense, this is a cantilevered, timbered porch that is hanging off the side of a double stack panelized wall. So we can do a lot of commercial applications. This doesn't just have to be for small ADUs. That's just our market. But this is also our market. This can also be used for much broader, more commercial applications as well. This is why we pivoted to this. For a very long time, we're building like 1 to 3 houses a year. That was great. No mechanism for scale. We tried doing workforce development in multiple different institutions for a decade and got nowhere, especially after the recession. We saw you couldn't even find carpenters, let alone people that were willing to try to learn how to build with straw and do hand plastering application. So we pivoted to prefabrication as a mechanism of being able to get more carbon stored in more buildings. We're now over 400% increase, and we're expecting that to go even higher in terms of the number of homes we're able to touch every year. And the cost is the other piece. It was getting almost impossible to build any new high-performance construction in our region for less than $500 a square foot. It's usually somewhere between $600 and $800. And we were delivering at or below $400 a square foot with our panelized homes. High-performance, all-electric, non-toxic, all the trappings of quality we'd hope to see. So we feel really excited about the opportunities of combining high-performance construction, panelized project delivery, and biogenic materials as actually being able to de-risk these and amplify the benefits of these different opportunities around how we're changing and transforming the built environment. I'm behind the BEAM tool, so I like carbon numbers. And it was one of our goals. It was actually a mandate for us that we created a building that was net carbon storing on day 1 of operation. One of the ways we did that was through straw. Another way we did that is by putting our buildings up on helical piers. Our buildings are light. We can get away with that easily. It's also cheaper. It's also easier in a backyard. It's also way more flood resilient, which is the big resilience category that we have to manage in our region. So win, 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 win again on a structural approach that may seem esoteric or banal.
Can you explain what the beam tool is?
Oh, yes, thank you. Question is, can I explain what the BEAM tool is? So the BEAM tool is a material carbon emission estimator. So it basically allows you to look at all the materials in your building, figure out what the carbon impact, the emissions impact is, and sort of solve for those or optimize for carbon reduction. We go out of our way to value biogenic carbon storage and include a lot of materials that are biogenic in nature that aren't necessarily found in lots of other LCA tools like hemp and straw, and cork, and various things like that. It's a free tool. I'm actively redeveloping the tool to be way better than its current version. So if you've used it and are like, I don't like Google Sheets, neither do I, it's going to be great. Let me know if you are interested, and I can give you more information about the tool and what's coming up for the tool. This will just give you a quick peek in how this works. So we created this tool essentially as an advocacy platform for being able to enable biogenic materials to be visible in the market and incorporated into decarbonization strategies in the built environment. If it's not quantified and named, it's invisible and is not viable as a solution. So that was part of the ethos of the tool. So you can see in cellulose insulation, you're like, yeah, we know that's a thing. You can actually see what the gross emissions are. Those are the real emissions released into the atmosphere, what the storage potential is. And in this case, because it's short cycle, we're evaluating that as a negative emission. So we subtract that from the gross, and then we get the net. And you can see all these different materials and do a direct comparison across their different impact values for a given R value performance. Wood, it's more complicated. So we'll still show that there's a long cycle emission value, but you actually have to check the box. Is it okay to allocate a negative emission to that mass timber? Do you know where the wood came from? What was the forest management plan from that forest? Like, can you convince yourself that, oh yeah, no, that is the atmosphere benefited from that? Great, check the box. If you can't, maybe don't check the box, but it's probably still going to be better than steel or concrete. So this is how we can start to actually quantify this and make strategic decisions as we're doing material comparisons or building out assemblies or coming up with whole home solutions around carbon storage solutions. So this is the accounting side of all of this. And yes, this is not looking at the re-release of those emissions at the end of life. That is not part of this analysis, so big caveat and asterisk around that, depending on how you LCA nerds are doing your accounting. That's very important. Okay, I'm going to show a couple of case studies, show you some resources, and then we can go socialize. So I don't want to leave you the impression that this is only about like small little buildings. That's just where our sort of like roots are as a firm, and I wanted to give you something tangible. I do a ton of consulting work. I worked with Andy Shapiro in Energy Balance and McClay Architects, where we built out 34,000 square feet of dormitory and apartments for a residence-based high school in southern Vermont. 2 different buildings, 22 corners, and I think 6 different roofs. Not a fan, but still had some really good outcomes. So we did a very thorough analysis around this throughout the design phase. We looked at modeled the building as a code-based building using sort of like business as usual materials, and we worked with the CM to kind of define what they would typically use for all their materials. We looked at what that would be at the net zero ready level of performance that the building was actually designed and delivered at, and we see a bump because we're consuming more materials to achieve a better energy profile. And I wouldn't say that's bad. That might be a reasonable trade-off, as I sort of grimace as I use that language. I would never suggest that you downgrade the energy performance of a building, like basically under any circumstances. We're just suggesting you don't have to accept this bump. We also optimized for materials and had a lower embodied emissions profile for a building than even what the code minimum building would have been, because we cared and we thought about materials and we did the math and we figured out the cost-effective solutions. This did not break the bank. This was not a major cost impact on the building. There's a lot of cellulose. It's a double stud cellulose wall. It's not rocket science, and it's not particularly expensive, at least in our region. Some places cellulose is expensive. In our locale, it was not. I want to shout out Christopher Nielsen and Bruner Kott, who led a fabulous project that I was involved with for Amherst College, building out a lyceum. This was the first new build. It's actually a combination of adaptive reuse of an old brick building and then a bunch of new construction under their new climate action plan. So it was very much under a microscope to understand what the full climate impact of this building was. So from day one, we were looking at a full climate response approach to this building. And again, double stud cellulose construction in a 3-story institutional building. There was under a lot of pressure and evaluation from the third-party building enclosure commissioner, both through design and under construction. There's a ton of sensors built into this wall. There's a great team led by Diana, oh my gosh, I'm forgetting Diana's last name. Anyone that remembers, help me out of UMass Amherst. Find me later if you're interested and I'll give you her name. She's brilliant. Did all of the hygrothermal analysis in these cavities and found it is boring. Double stud cellulose walls work fine in institutional applications. There's nothing to see here in terms of like significant risk from a hydrothermal basis. So that type of research and innovation is super helpful in de-risking and normalizing the use of bio-based materials in commercial and institutional applications. We now have multiple case studies proving this out. And then a host of biopolymer carpets and a bunch of cellulose and really like demanding EPDs and getting really good data on all of the most intensive parts of the building. So there's a lot of really good case studies out there. Typical building may have been around 400 kilos of emission per meter squared. This came out in 200, not counting any of the carbon stored in the wood. If we did count the carbon stored in the wood, that would have been 70, that's basically zero from a margin of error perspective if we were able to credit all of the wood that was used in the structure for the embodied emissions of the products in the building. I didn't want you to leave you the impression either that straw is only for use in small residential applications. That's just in the US because we are literally a generation behind Europe in their application of straw, and we are like hundreds of years behind the entire like non-industrialized world that has been using these materials consistently and successfully in large-scale applications. I'm just going to point towards our like closest neighbors here in France that are like now have like dozens and dozens of public schools that are built from prefabricated straw, largely because of their health benefits. This is like standard construction now. There was I think, was it 100,000 square meter logistics center just built out of straw panels in Scandinavia, Denmark, I want to say, or Sweden, one of those 2 countries. Like, this is not a technological problem. This is a matter of us catching up with what is becoming standard practice in many other parts of the world. I'm also looking at this very heavily from a climate lens. If it's not clear at this point, let me be very explicit. There is a stack of benefits that associates around. I've already talked about toxicity and human health, the ability to achieve high performance design with these materials. My experience in working with straw for 25 years, it is way more resistant to moisture infiltration in buildings than fiberglass insulation. Foam insulation, the foam may be fine, but then all that moisture risk is pushed onto the adjacent sheathing or framing. Like I have high levels of confidence in working with these bio-based materials and achieving durability and performance and all these other values. I do want to pause for a second and talk about climate justice. This is the first time I've presented kind of with a bit of an open platform since June, when one of our co-owners and one of our managers at New Frameworks was illegally and violently detained by the federal government. And for those of you that know the story and have been supporting our company, I greatly appreciate that. I bring that up because that actually really matters in practically adapting these strategies. There is the policies around not just, especially immigration, but also fiscal policy that we are now, let alone climate policy, that we're now operating under, are a direct harm to our industry, to our workforce, to housing policy, to the economic environment in which we're trying to address these really critical issues. We've seen this repeatedly. It is a bit frustrating to me to not see the building industry actually calling out the direct harms that are coming from immigration policy, just purely from a workforce development and economic basis, let alone human rights. Like, if that's too political and we want to put that to the side, fine, we can just talk about the economic and workforce impacts of these policies. If we're not talking about that, I'm talking about this now because if we don't talk about this, it becomes normalized. It is not normal, it is not acceptable, it is harming all of us in our industry, and we need to say that out loud and repeatedly so that we don't just comply in advance and allow these policies to persist and just try to like slip under the radar and hope it doesn't somehow land for us. It landed for us directly and continues to dramatically impact our company and our community professionally, and is only going to increase in the risk that we all face in trying to achieve climate goals. We cannot decouple the human rights abuses we're seeing in this country from climate action. Ecological and social impact are not separate, they are the same. Humans are part of the climate, part of ecology, and these policies are harming comprehensively across the board the same way that these materials have a stack of benefits. So it just feels really important that we call that out and say this out loud. I appreciate you creating a little bit of space to be able to make some of this out loud and visible. Thank you. All right, I'm going to move us towards the end here. I'm probably already blown past our time. The other thing that we're doing, so scale. So I want to continue to scale is like the big thing we're all talking about because we're in crisis and trying to move quickly and make really big moves rapidly. My concern is if we only look at scale from a 20th century model of industrialization, we're just going to replicate the same patterns of harm that got us into this case in the first place. So we are looking for other models at which we can influence change and transformation in the industry. What we see is rather than just growing out in scale to be the largest panel producer in North America, is we'd rather see a broad distributed network of cooperatively organized panel fabricators across North America that can respond to the material bases and cultural and economic bases in their regions and provide housing and panelization and material solutions in their regions. But the information that we benefit from has been open source since its origin, and we see no reason to stop that flow of information. So we started a training program to help stand up other fabricators across North America. So in the first year, within the SEED program, two companies, Building Integrity and Rare Forms, transitioned as a building company into a panelizing company. Building Integrity was an architect, an engineer, and a construction company that came together to start a new fabrication company. Within 1 year, they were both serving the market, and they are now members of the SEED Collaborative. So we're now sharing marketing resources, lead sharing. We're starting to explore some co-manufacturing. We're starting to co-invest in research and development in ways that any one of us small companies would not have the ability and capacity to absorb. Year 2 of the program, we now have 3 more companies across North America. So we're now, by the spring, there'll now be 6 fabricators nationwide that are part of this network, and we have a wait list for the following year. And some of these are indigenous communities looking to self-provide housing solutions for their communities. Some of these are regions in Southern California that are trying to come up with fire response solutions based on their regional archetypes and material availability. So this is our vision, our theory of change, and our vision for industry transformation is through more of a horizontally distributed cooperative approach towards manufacturing and reducing the scale and increasing the open source transfer of knowledge and capacity across our industry in that regard. And one more tack at scale here. So we model out, actually every copy of Beam comes with this model, the DOE model home, and what its standard approach is for using business as usual materials, which releases about 33 metric tons of emissions in building a standard model home. If we were to hypermile, totally optimized for carbon storage, we could, with existing materials on the market that we have all literally built, all of us in our community have built with, we can have 6 tons of storage heading into day one. So great, that's nice at the scale of one building. I know I'm talking to a largely commercial environment here. I'm going to make an analogy in a minute, so bear with me. If we look at the projected need for housing within the Northeast by 2040, and this is sort of an accumulation of state level housing, sort of like housing growth requirements or projections for each of these states, we got about 2 million new units required in our region. So what's the impact of that if we're using business as usual to address the housing crisis? Well, if we're using sort of the worst case, which is business as usual, that's like putting 20 new coal plants online between now and 2040. If we can even achieve this, because 1/3 of our labor force is under risk of deportation. But if we can actually do this, we are going to decimate any hope of meeting any of our climate goals. You're working with business as usual materials. But if we take on the challenge of solving for both problems, we can both be removing carbon dioxide from the atmosphere and storing it in the fabric of the built environment as we're developing those housing solutions. So if we're talking about scaling this up in the context of like low-rise, light, small buildings, those of you working in the commercial space can imagine how that amplifies its scale when you're working at buildings at larger scale. Granted, storage is way harder in commercial buildings, but just looking at the opportunities for impact reduction in the material basis as we're continuing to build out more and more commercial non-residential fabric or larger residential buildings, which seems to be a very growing trend around addressing our housing solutions, this really, really matters. So just imagine this ballooning out in scale as our buildings get larger. Okay. I'm going to move through this relatively quickly. This is largely resource sharing and inspiration. So don't panic if I'm like blasting through these resources kind of quickly. They're all going to be captured by the magic of video, and I'll share the slide deck out. But I'm going to bring us into conclusion here. Like 10 years ago, we were still trying to even figure out like what embodied carbon is. Do we care? How do we even measure it? Like what is this? And within a decade, we've gotten to the point of like having a sense of scale, knowing what the basic hotspots are, having like some basic prescriptive, like low-hanging fruit, like solutions we can use, and a bevy of tools in the market to analyze this. That is lightning fast relative to those of us that have been in the like energy world forever. And so this is where we are now. And I'm going to speak from the residential perspective just as a case study, and I'll talk about some non-residential situations as well. There is now a standard that's about to emerge I'll talk about that'll standardize how we do this evaluation for residential construction. That is crucial because that will now enable the ability to start setting some regulatory structures around requiring that reporting. We're already seeing that in the commercial space. Commercial space is ahead on that, which will then lead to limits and then actually get us towards the reality of carbon storing buildings. It's not enough to have the technical solutions. We need the economic and regulatory structures to be able to compel those solutions to be used. So Resident Standard 1550 is huge. It fills this enormous gap in the low-rise residential space, which is basically entirely off the radar for most of the, both the analysis and research as well as the sort of soft cost availability for these projects to be analyzed. We're on the verge of having this be enacted not just as a standard that a consultant or an engineer can follow, because that's useless in the majority of residential construction, which may not even have architectural services, let alone a BIM model that can have information flow into a tool. This is going to be done by energy raters. And that is the community that is most dramatically, or the most readily touching these buildings. It is also a direct link from a single knowledge source between energy and operational emissions and embodied emissions, which is the whole thesis behind this, is that we need to look at these things together to make our best solutions. Now we have a workforce that is trained around analyzing buildings that can expand their scope from energy to material assessment and bring that into a harmonized workflow, tool stack, and communication stream throughout the entire project delivery process, which is particularly valuable for production home builders, which is how the majority of residential construction is built in the US. So huge opportunities to unlock all of this development of scale by just standardizing how we all look at the same thing. This is tremendously exciting. To the point that I'm going to talk about a couple of Massachusetts specific things, since this is a mass crowd. Thank you, my friend. We just completed, the report will be released by the end of the year, a 100-home benchmarking study, where not only do we benchmark 100 homes in Massachusetts to actually get a good walking around number that we can now base our incentives and regulatory structures around, but we also did some very rigorous testing of the standard to make sure that there was an iteration process of the standard as it's under development, to work through industry preparedness and workflow development for raters to be able to understand how they're going to conduct this analysis. And for us as tool providers, me with Builders for Climate Action, working with Ecotrope as an energy rating software, to figure out what tool integration looks like and really take the friction out of the process of moving an information flow from a rater taking inputs from a building and push that all the way through getting an embodied carbon metric. So like we are well along the way in actually conducting this work and having low friction, high volume, scalable assessments in all of these buildings. This is thrilling in terms of the capacity for being able to really transform the industry and being able to bring this metric into our purview. So again, those of you that have worked with BEAM and are mildly or majorly disappointed with its performance, I'm so excited to say that we're going to have a 1550 compliant energy model tool integrated version of this software coming out within the near future. So if you're a software geek, talk to me and we'll nerd out over drinks. There's also really exciting stuff happening in the non-residential space. This is even larger. I'm going to talk to resources that will get you more of those resources. I wanted to call out the non-residential counterpart to 1550 is ASHRAE 240P that is undergoing review right now. That's going to be a long and winding road to its delivery, but there is a unified standard that's looking at both operational and embodied carbon emissions within a unified standard. Again, really important to learn how we can look at those things together. So if you're on the non-res side and want to look at a standard for this, it's still under draft development, but it's exciting to see. And just the amount of resources that are coming up. I'm bringing up MEP 2040 is a collective impact organization that is addressing how to deal with emissions from mechanical, electrical, and plumbing. They just released a beginner's guide on how to just start conducting this stuff. And what's really cool about that is that that is going to inform standards like this, which are going to codify best practices like that. And there's an iteration cycle around our knowledge base and our policy development and our practical application that is really accelerating the adoption and the quality and the rate of all of this knowledge and practical application. That is thrilling. That's really, really exciting. So just seeing that both of those two things exist and inform each other is a really important pattern for us to recognize. I'm going to call out Michelle Lambert, you didn't know I was going to do this, but thank you as a representative of Carbon Leadership Forum, who's been instrumental in developing policy visibility as well as policy toolkits around how we can enact more and more of these policies. Toolkits, maps, an amazing compendium of case studies. I'm bringing up the map just to highlight within Massachusetts, all of these embodied carbon policies exist within the state right now. That level of precedent and that level of development is, again, thrilling. This is really, really, really exciting to see this matriculating into policy already, and then the iteration between policy and practice and how rapidly those things are informing each other. So y'all working in Massachusetts are at the front lines of the development of this practice, and it is really exciting. So I'm putting up this slide just to identify how many different impact organizations are working in this space right now. It is amazing. So architects in the room, raise your hands. Great, Architecture 2030, AIA, Material Pledge. There's a bevy of different organizations you can be involved with. Contractors in the room, Contractors Pledge. There for you, Contractors Commitment, as well as Home Builders Can out of RMI if you happen to be on the residential side. Architects in the room. I'm sorry, engineers. Thank you, we did that already. Engineers? Structural engineers? All right, quiet. Well, all your structural engineer consultants, point them towards SE 2050, MEP 2040 for the mechanical engineers. There's a group for infrastructure people, for landscape folks. Like there is something for everyone to get involved with, to be actively part of this work. And it's not just because there's an obligation, it's because we need that. We are so isolated and siloed in our practices, in our lives as individuals. It is the most painful thing that I hear from people, is the feeling of isolation and overwhelm, and how hard it is to like face these existential crises without agency and without community. And this is not just like, oh, now there's a way that you can do this thing. No, we all need these communities of practice to be able to bolster our ability to wake up in the morning and face hard problems. So like, see this as an opportunity for support as much as a imperative for engagement. And the ECHO project is an incredible project. Again, shout out Michelle for being the current sort of facilitator or convener of this, bringing all these organizations together to harmonize how we're assessing embodied carbon and getting our methodologies consistent across the entire industry. That level of radical collaboration is not endemic to the culture of the AEC industry. So the fact that this even exists is transformative in nature and highlights that these are not just technical problems to solve, these are cultural problems. And by addressing this on a cultural level, we can achieve scale and enact that much more opportunity in the work that we're doing. A couple more organizations closer to home, the Bio-Based Materials Collective. If you really are jazzed about bio-based materials, or you fall in love with the petting zoo, join us. It is the most fun and nerdy group of material enthusiasts you'll have the opportunity to work with. The CLF has a local chapter, Boston Northeast chapter. Such a high-power group of people. Like, oh my, and again, some of the most like engaging, brilliant, heart-centered, and like passionate professionals you'll hope to be in collegiate with. So join us, it's awesome. And you are here right now. Like, you're here by choice. You are part of this work. You can like now self-identify as being part of a movement. If you already know that, you are a leader in this movement. Find someone in this room you don't recognize and help invite them in. If you are new into this space, welcome. You can't unlearn what you saw today, and we encourage you to continue to join us along this path, because it is the antidote to despair, is action and is community. Shameless plug, if you want to learn more, I'm teaching a course tomorrow through the Material Matters training series. Laurel gave a great presentation a week ago, 2 weeks ago, a couple weeks ago. Lisa, you're going to be giving a talk coming up soon. It's a great series. Some amazing people are involved with this, so check that out. All right, I'm going to leave us with a couple of metaphors and then let us go. Thank you for your patience. I know we went on for a really long time here. This is useful to me for a couple of reasons. One, it's always helpful to remember what we're doing this for. It's so easy to get caught in metrics or in theory. But we're here because we live in places that we love, and we love people who live in these places. And that is the imperative for why we're doing this work. This image in particular feels very useful for me. I know that I have felt significant amounts of despair over the course of the last 6 months, and literally feel like we're moving backwards. And work that we've been investing in for years is being dismantled. It can be really defeating and disorienting. What I've learned about this work of transformational change is that it is non-linear and it is emergent. We don't know what is going to happen, and it is not going to be in the direction of the North Star that we see ourselves needing to arrive at. But any of us that's, I'm a paddler, if anyone that's like been on a river trip, you know that like you go around an oxbow and you're literally going back in the direction you came from. But you know that the river is leading out of the valley. There is a direction that you're moving towards. The benefit in these trips is that we have a map. We don't have a map, but we can have faith and trust that the path is non-linear, but will take us towards a North Star if we can be clear on the direction that we're going. And those of us in a permaculture space know that we're just creating more edge. It's just more opportunity for information and nutrient transfer. There is actual value to this not just being a straight linear path. And so we need each other to be able to find our way along that path. And we can look at another metaphor from nature where we see the incredible relationship between communities of trees and communities of mycorrhizal fungi living within the soil. These massive aerial macrobiotic communities with these invisible subterranean fungal communities that work in brilliant symbiosis to exchange information and nutrients and water and minerals across this vast network, and that is a brilliant model for how we find our way forward. It is not within our silos. It is not by being a hero or under the gates of IP. It is through information and knowledge sharing and exchange, emotional support, and collective impact for wayfinding through the complexities that we're facing. I'm going to move past this because we do not have time, but if anyone wants to talk about tulips with me later, we can do that. So I'll just say thank you for your attention and your time, and it's an honor and pleasure to be with you today.